presently we are discussing the bulk nanomaterials preparation, and we have seen it earlier. With the strength and toughness of the materials varies like that in usual materials, and this shift towards the right hand side if there is the grains are refined, and in the nano stage it is a considerable shift occurs, and with this criteria the strength with the same strength with the toughness of the materials become quite high, or if the toughness remain the same, then the strength is also going to be very high. So this criteria is uses for the development of bulk nanomaterials for the structural applications. If you the strength and the grain size in this material is dependent on this famous equation, which is called the Hall-Page relationship between the yield stress and the grain size. It shows that the yield stress of a material depends on the inversely dependent on the square root of the size of the materials, that is the grain diameter. In this equation, actually, the Ky is a constant, and it depends on the material to material, and sigma 0 is the yield stress at the normal conditions of the material. So sigma y is equal to sigma 0 plus Qy by root of d. D is the grain diameter of the materials. So the entire nanostructured materials for structural application is dependent based on this equation, which is a very famous equation known as the Hall-Page equation, which is quite common for the material scientists. So today we will discuss a technique which is called the severe plastic deformation of metals. So we will take the metal or the metallic materials and we'll give a severe plastic deformation, which is known as the SPD. It is one of the top-down approach of nanomaterials production, which refines the coarse-grained metallic materials into a nanostructured materials. But it cannot go in one stages to that. It requires a various stages to go to the area of the nanostructured materials. So there are different categories for the severe plastic deformation. One is that equal channel angular pressing. It is the very popular one, equal channel angular pressing, or the ECAP. Another one is the high pressure torsion, and there are various techniques. These three are is very popular for the materials engineer. That is the equichannel angular pressing, high pressure torsion, and accumulative roll bonding, ARB. What is this equichannel angular pressing? ECAP, it works by introducing a large shear strain by repeated extrusion of the strain. Extrusion is a very common in a materials scientist, a materials engineer. A Extrusion is basically to pass a material through a die whose diameter is less than the initial diameter of that material. For a long time, this extrusion technique was used for drawing of wire. So wire which was casted in a casting in a casting company that can be drawn at various sizes of the diameter at different for for final application, and that was the technique by which extrusion is the technique by which the wires are drawn at various diameters from the initial diameter of the material. So ECAP works by introducing a large shear strain. Shear strain, I think you understand by the shear strain, by repeated extrusion steps. Do you understand what is the shear strain? Do you have any idea about the shear strain?
So, like, due to applied that bending, there is a change in that dimension. So,
It is the strain which is given by the between the two layers. Okay, so when you are giving the strain, that is, we always think to giving in one direction along the length of the material. But here, the strain is coming between the various layers. So the crystal structure, which is having in the material, is completely destroyed and giving the size of the material in a different forms. It is the strain is given between the different layers. Um, um, you just think of a system. There are two layers. Just look my hand, and the shear is between these two one. There is a split between the two plates. This is going one, and I am giving a stress along this direction, So this is the shear. Okay. Clear? No? What is the shear strain?
yes, sir.
Yes.
Yes.
So ECAP works by introducing a large shear strain by repeated extrusion steps. It is one of the most commonly used severe plastic deformation process to drive nano or ultrafine grained microstructure at low homologous temperatures. What do you mean by the homologous temperature? Homologous temperature is the temperature of a material which is the fraction of the melting point in Kelvin scale. Means this can be carried out at relatively low temperature compared to this melting point. Initially, it was tried at the room temperature, but slowly people tried to heat it at a elevated temperature, but not to the melting point, much below the elevated temperature. Usually, this homologous temperature varies from 0.3 to 0.5 for this ECAP. So homologous temperature is the temperature of the material as a fraction of the melting point is in Kelvin scale. It varies from 0 to 1, and ECAP is usually carried out from 0.3 to 0.5. So what is happening here? The ECAP involves introducing large shear strain in the workpiece by pushing it through the die that consists of two channels with the same cross section. You see, this is one channel, this is one channel, and this is another channel. So here we will push this material into this channel, and there will be a total huge amount of shear stress is generating here, and we are coming out from this material also. So ECAP process introducing large shear strain in workpiece by pushing it through a die that constant. This is the die, this is the die, and it is the die, and there is a hollow region die that consists of two channels with the same cross-sectional shape that makes that angle to each other, that makes an angle to each other. The two angles are very important here. One is this angle phi and one in the angle psi. So the internal channel of the die is bent through an abrupt angle phi, and there is an additional angle psi which represents the outer arc of the curvature as the two channels intersect. So there, a lot of mathematical calculations was made depending on the phi and the psi, and what is the effect of that on the material properties. The sample in the form of rod, bar, or square shape is machined to fit within the channel, and the sample is pressed through the die with a plunger. So let us see how it occurs. So for demonstration, I put the die like that. So this is my sample, and this is my plunger. The microstructure of this material is like that. It's quite big. Precipitates are there. And if we go on the process slowly, and you see how much plastic deformation is taking place at the channel where is bending is occurring, and this process, and it comes in the same shape what was the initial materials. So this is that microstructures after ECAP, and this process can be repeated various time, so that at each stage there is a refinement of microstructures, and this refinement goes to the nanoscale after different after suitable passes through this channel. So, since the cross-section of the two channels are the same, the extrude process can be reinserted in the entrance channel and pushed again through the die. We always try to put whatever the initial part and the end part is the same, so that the same can be again put it and give that deformation. Repeated extrusion through the ECAP die accumulates sufficient strain to break down the microstructure and produce ultra fine grain size. So, again that same equation, the ultra grain microstructure of the metals improve their strength according to the Hall-Page relationship between the yield strength and root of the grain size. So these are the some results. This is that copper sample, and with the copper sample, and you see how with the number of passes, the yield stress of the material changes. It changes. Initially, it was 260 megapascal. Then with that process, it goes to 300, 345, 360, 380. Maximum it goes to 390. And after that, it started decreasing. Not only it changes the strength of the material, it also changes the functional properties, that is the electrical conductivity of this material. So with the number of passes, there is a change in electrical conductivity of the materials. This is an example. This is an example of aluminium, zinc, magnesium alloy and the corresponding TEM structure. This is that initially that adhesive material. This is after one pass. This is after 4 pass, and you see this is after 8 passes. So how this equichannel ECAP process, equichannel pressing process, changes the microstructures from usual crystalline microstructure to the nanostructured materials. And with this change of microstructures or the formation of the nano precipitates, all the nano grains improve their properties quite high. It increased the structural properties like the strain toughness, and also in some functional materials, it improves the functional properties also. What is an advantage of the ECAP? ECAP technique is capable of producing bulk nanostructured materials. That is the one advantage. What is the other advantage? It is the nanostructured material produced by ECAP are 100% dense. That is very, very important. Is density does not change with this process. So nanostructured material produced by ECAP are 100% dense. This is the important mechanical properties and contamination free, important for many of the applications, for example, the biomedical applications. So through this process, the density of this material doesn't change, and there is no contamination in this process. But there is also a disadvantage. When there is an advantage, there is also some disadvantage. The major disadvantage is that it generates a lot of defects in pressurized sample. It generates a lot of defects in the pressurized sample. It introduces a lot of internal stresses. Not only it's due to this highly deformations, the dislocation density within the materials become very high. Sometimes fracture after some passes, it gets fractured at some passes. And this also can be tried to minimize by giving a extra pressure from the outer channel. So we are giving a punch through this pressure through this one and giving an extra pressure from the other side. And with that, this gives an indication that this is a magnesium sample, and when there is a crack, without this is no back pressure, and if we give a pressure, the same one give that there was no fracture at the ends. There's another disadvantage, this process taking a long time, and for that the productivity process is less. Moreover, we cannot go for this one very large pieces. So it has to be small pieces, but a large number of pieces. The um, what I call the grain size was further uh, reduced by a process which is called high pressure torsion. This is also a severe plastic deformation process. It's a high pressure torsion. And what is there actually? The material in this case has to be put in between two anvil, and you have to give a pressure through this anvil, and at the same time you have to give a twist. So there is a rotation here. So this rotate along this direction and this rotate along the other direction. So there is a twist. Yeah, that's why I call high pressure torsion HPT. The grain was further refined. So whatever the refinement we got in ECAP, but if we use this high pressure torsion, the grain are further refined using high pressure torsion technique, in which the applied pressure was eventually high and compared to the ECAP process. But in this case also you can understand it is not able to produce a large materials, a small materials, but number can be high. And here also the limitation that we cannot give pressure more than what is the yield stress of this anvil. So there is also a limitation of this technique. Okay. The channel of what we are seeing, this channel can also be in the twisted form to get it much more refinement of the grains on the precipitates. It is something like that. And by this technique also, we can get different shape of these materials. Of this twisted one, we can also get different shape of this material also. See, we have read it that the strength or the hardness of the material changes with the square root of the grain size. So if we go on, there will be it should go infinitely, but it was observed that there is a limitation. It should not go after some time, it try to get its saturation value. So it is not that the Hall Page equations what we have seen is the true for the entire diameter of the entire grain size, but after that, after a critical one, it try to saturate, and uh, we cannot get more hardness after a critical diameter related to that particular materials. So Hall Page equation does not valid to entire range of the grain size. There is a limitation. This is the limitation of the Hall Page equation. What is an application of this ECAP process? ECAP process has paved a path to synthesis of large billets and hard to deform titanium alloys. Titanium alloys giving the deformation is quite hard, but through ECAP process, we can get a near shape of this alloy with ultrafine and consisting of uniform size distribution, which focus mainly on the stress deformed state, contact stress, and the friction. These are the different applications of the material produced through ECAP process. That is the titanium alloy. Titanium alloy is very suitable for biomedical application. Mainly, this titanium is compatible with our body. So these are the some of this application. The dental implants. This is the denture framework. These are the framework which is also made from this um, titanium alloys, and also complete denture bases. This is the basis. There is more applications of this titanium alloys for biomedical area. That is this commercially pure titanium is the artificial valve, replacement of joints, dental implants, stents used in blood vessel. This material in its normal state was also used for these applications, but with the application of nanostructured, the strength of this material increases fewfold. Similarly, this one, titanium, aluminum, vanadium, is artificial bones, synthetic joints, and dental implants. These titanium, niobium, tantalum, and zirconium, this one is artificial bones and artificial joints. Titanium, aluminum, and niobium alloy are used for the medical and surgical devices. It is used for the hip joints, artificial joints, and dental applications. So these are the some of the references you can get. Particularly, this is a quite good reference. I don't know from where you can get this correlation between the defect structure and mechanical properties of nanocrystalline materials. This is a book that defect structure in nanomaterials. Any questions from your side? What the question? Do this material used for medical implant does not affect the body tissues? No, no, it will not affect the body tissues because you see the titanium is type of material whose what we call actually Young's modulus is compared to our bone structures, is a comparable actually. So that is why titanium is used, not the other materials. Its toughness is comparable to our bones. Yes, Ronald?
So, like while talking for the medical application, like what are the parameters we have to talk upon or look upon?
Yes, one is the toughness we have to see, and foremost we have to check whether this material is reacting with our body. That is the foremost uh, uh, thing we have to see, whether that material is have reactions with our body. Second is that a toughness should not disturb our tissues or the related bones. It should be of comparable natures. And There is another most important that tissue can also grow on this type of materials, or that you have to also check actually.
So, sir,
What are the other things we have to? I have to read and I have to tell you. Okay.
okay, sir. Okay, sir.
Okay. There are the quite stringent requirement for any biomedical application. There is quite stringent requirement for any biomedical application.
Okay, sir. Okay, thank you.
You see, whenever in the biomedical applications, if you develop a material, it will not be used immediately. It has to go through a several tests, and some authorized agency has to certify that yes, this is compatible to your body, and then only you can use. So any medical application, the material has to be developed quite early, and it takes a long process for this testing actually. That is in vivo testing, this is in vitro testing also. Okay.
Yes, sir. Yes, sir.
Any question from other side? Bhavika, you have any question?
No, sir.
So some of you probably are recording it. Am I right?
I'm doing the recording.
Okay, Durga, you are doing. So this is actually what we discussed today is the severe plastic deformation, which is also a top-down approach. And now in the next class, we will discuss other methodology and their product, and there are specific methodologies used for development of specific product. That is also important in the area of nanostructured materials. Okay, then we'll close today, Dr. Durga.
Yeah, sure.
Huh?
Yeah. Okay. So thank you, everyone. So we'll continue tomorrow, or
No, I'll not continue tomorrow. Maybe next
so
week.
next
Durga?
week. Yeah.
Next
Okay.
week.
Okay.
If any of you has some question, please ask. I think as Durga, you are sending this recorded version to all
Yes,
the
I mean
students.
I will share it today. So yesterday I have not shared, so I will do it today. Yeah.
So in that case, I don't feel that we require this PPT to send all the students.
I don't think so. I think the recording should be good enough.
Huh? Can
hope,
the students
yeah.
can respond?
The recording is enough.
Recording is sufficient. Am I right?
Yes. Yes, sir.
Okay, very good.
Sir, if the PPT is sent to us, then it is also helpful.
Okay, then I will few classes together and will send you the PPT then. Whatever you tell, I don't have any problem. I can send you the PPT.
Okay, sir, please share this PPT. so that we can go through it and read them topics.
Okay. Okay.
Thank you, sir.
Okay then.
Good morning, sir.
Good morning.
Sir, I have one question that
Sure.
using this ECAP method, can we get some specific type of nanostructures like for very varied applications? At times we need needle-shaped structures, or for super hydrophobic surfaces, we need micro nanostructured surfaces. So is it
Yes.
possible to get on depending on our application, like what kind of structures we need, can we get them using ECAP method?
Yeah, you can get a shape, your required shape. But you see, if you want to get a, just now you told this hydrophobic. So you require, in that case, after getting this material, you require a special surface treatment or some sorts of coating. So through ECAP method, you cannot get a material which is hydrophobic. So you can get a base material on which you have to treat in such a way that it is hydrophobic or hydrophilic.
Okay, sir.
Okay.
Yes,
So
sir.
this is the method, only it will change your microstructures and you can get advantage of finer grain. Usually, many functional materials are not prepared through this, although it has shown some functional properties, but usually it's not prepared. Most of this application is basically is the structural materials and mostly the structural materials.
Okay, sir. Thank you.
Okay, then I am closing it.
Yeah, so we can
Okay.
stop for this.
Thank you very much to all the students. We'll see you in the next week.